Thank you, folks. So the title was the conference's best kept secret until just now. I'm going to talk about the recent DEEP 1016 and its revision that Manu, Walter, and myself worked on, with credits due to Manu, who raised the issue for only about like 10 years. And also DEEP 1016, and Walter did a lot of detailed work on specification and implementation and evaluation. Walter was also instrumental in actually looking at the compiler code to see the exact rules, which were formerly undocumented. So he was a great resource for that. There are two motivations for allowing binding rvalues to, there are two reasons for putting ref in the function, in a function signature. The first obvious reason is that the function wants to manipulate the parameter as a sort of semi-side defect. So you pass the parameter by reference, the function takes it, messes with it, gives it back to you, and everybody's happy. Reason number two is that the function would like to take or return a large object efficiently. So it wants to take the address of the object instead of taking a large object. And when I say large, it's, I'm not talking necessarily about, I should say elaborate here. What would be the difference? I mean, when could be a small object creating problems with passing by value? Please.
Copy constructors.
Thank you. So the object may have a copy constructor which has, its cost, which is, not necessarily bounded. So actually, there's been a number of studies on reference-counted languages, and it turns out that simply, bumping a reference count, seemingly a very cheap operation, just bumping the reference count whenever you copy the object into a function and bumping it down whenever you return from a function, turns out to be quite costly at scale. I remember the running joke of the Lisp language started as reference counted, and it was really slow, and it was inoperable, and then there's a cycles problem as well, and I'm talking about like the 70s, right? And then the implementation switched to a tracing-based garbage collector, and the garbage collector, as Walter said, has a different it makes it fast whenever the thing goes, but when it starts to collect things, you gotta stop. So what many engineers did in that era was whenever the garbage collector would start running and pause the application, they would reboot the machine and start again. And it would be faster that way. At any rate, these effects of even a seemingly small operation, whenever applied at scale, they're going to exact a large cost. So we want to make sure that we are able to take and return a large object, an elaborate object efficiently. And now the problem is that the language was designed to cater for these guys and allow these guys as a distraction. I take the silence as a nod of agreement, right? So if you happen to have an L value that is there and it's just passive by reference, the command is going to be fine. I assume you're going to want to change it even if the function just cares about efficiency and it all works. But if you actually have a function returning a temporary, then you have a problem. We discussed this. Actually, sort of the standard cop-out would be, well, if you want to pass things around by address, why don't you simply use pointers? And using actual pointers is, clunky in syntax and also unsafe. There's a lot more tight scope duration control with references than with pointers. And the language keep on worrying that the side effects are going to last, and then it's going to put barriers in your way. To go with an example, let's assume we have sort of I don't know, drawing system with a shifting coordinate origin. So the origin is actually a function call. It's not always 0, 0, 0. It may actually shift the origin to wherever you want, so you can draw wherever you want. So then to compute a distance between 2 points, maybe you take things like two reference to constant point objects. That would be your distance primitive, and it returns, for example, the Euclidean distance between the two. Not a problem. But very often we want to take the distance from a point to the origin, right? AKA the norm of a point, or essentially like how far am I from the origin of coordinates. And what I want to write is the distance between P and function called origin. What I must do is put the origin in a temporary like an idiot, pass the temporary into the function, and then move on with my life, which is an unpleasant thing to do. And what would be a better solution to this instead of having the caller always using these nice temporaries? What would be, you're an engineer. You should.
Have the machine do it.
Sorry?
Have the machine do it. Like the machine could create the temporary form instead of me.
No, not engineer, I said. What can I do as an API writer of distance? So I'm defining the API of distance. And I want to, yes, overloading. Thank you very much, Kai. So I want to overload. And all of a sudden, I have a page full of code on my hands. So we have the actual implementation, which does the heavy duty work. That would be Euclidean distance or what have you. So this would be the work. Everything else is scaffolding, boilerplate, bad things. Yes? Like these are the bad things. And essentially it scales with 2 to the power of n, where n is the number of parameters you want to bind to reference or value. And I saw this is an expression like in British English, which means kind of disgust or kind of something not nice. Is that right, James? Like whatever. Oi. All right. So it scales really poorly. This was a known problem in C++ as well, and it's definitely not something we want to proselytize as the normal course of doing things in the D language. It's not nice. Speaking of C++, there's working related languages, and I think having a good understanding of this related work is seminal to developing a good solution that works for the D language. So in C++ is the obvious, receptacle of existing work because since the early days of C++, and I kind of actually looked in the books and articles at the time, it was very early on understood that you want to bind rvalues to const reference to t. Sorry, to references to const t. So that became actually fundamental, and in a way, it became too fundamental because the conversion from an R value of type t to reference to const t has become so tight in C++. I think it's a const conversion. It's like the cheapest the least friction path you get in any conversion. So that being the cheapest way to convert things, it's so tight you cannot overload on left values and R values. And that turned out to be a disaster. Because functions could not, so the first thing that happened with C++ was people defined templates. And the next thing that happened, people wanted to use templates to detect whether an argument is an R value or an L value. And you can't do that because the moment you have an R value, it's going to immediately go to const t reference without minding that there might be a better match, better function match that would take an R value. So this became really, really bad. And it became so bad that I've done some work on a library called Mojo, which relied on some obscure language idiosyncrasy to do that detection, but it was not very easy to use, and it was incomplete. So a large part of the motivation for rvalue references in C++ was this very fact that very way back in the 80s, this decision was made, well, let's make rvalues to const a very, very, very cheap conversion. So we want to kind of take the nice parts of this, but we don't want to make it too tight. We still want to overload on rvalue and lvalue. So this is the lesson that we take from here. Another language that has previous work on this is Rust, which does allow rvalues to bind to ref, but you need to place syntax on the caller side. So you're gonna put like this mutable, reference to mutable 42. So even if 42 is an R value, you're gonna put reference to mutable. And I spoke to Manu and Walter about this, and Manu said, wait. So first of all, like in generic code, do I put this or not? Because usually you have like a function call here, and you don't know exactly what the function returns. Is it an R value or an L value? What's is it a reference or not? So do I put it everywhere? Just to make sure, or do I put it conditionally? Do I do some introspection to see, oh, is that an L value? So my code is going to look like a patchwork of. Do I put this symbol? For D, it would be ref, right? You put ref here, right? So you put ref 42, right? For a simple example, it looks okay. But for generic examples, it would be quite difficult to figure out when it makes sense and when it doesn't. So we don't want to do that either. So that's not generic. So these issues have been a large problem for us for years because we didn't know a way out of this. The simple solution to cut the Gordian knot would be they simply relax the rule and go with the flow. Let's say, ref accepts our values, and like my kid when he was learning chess, he would know the moves, and he would make his strategy in chess was he moved a piece correctly, and then he would start analyzing the new situation on the board. Right? So let's make the move and analyze the situation that results. Not too good. So looking at Strauss-Trup design and evolution of the C++ language, he has a very nice example that's it's simple and illustrates the problem. It would be, well, what if I have a function that simply increments a counter, maybe logs it or does it in an atomic way or whatnot, so it does some increment with benefits. And then we have an integer counter, and then I'm going to bump the counter. So int to long is an implicit conversion, and again, very low friction. And then, if the code compiled, actually counter would be unmodified. And worse, we have fragility in face of change. Because what if this was int initially, the code works, it compiles and runs, and then you change it to long, it still compiles and runs, it just doesn't do anything. Because you convert the int to long, a temporary long. The temporary will be incremented, the temporary goes away when the function returns, nothing happened. All right, solutions? We are engineers.
Overloads.
No. 2 for 2. Yes, please.
Ref has to disable implicit conversions.
Yeah, so how about this? Keyword being except. So, let's do just allow the conversion, except when they originate from L values by means of implicit conversion. And if I learned anything from language design, is whenever I see an except, you gotta be worried. It's worrisome. So, I looked at this and thought, there's something wrong with this. This is not covering everything. And indeed so. Consider a simple code evolution where we have like some widget and it has a price. It's a public state variable. And we discount the price. We multiply it by 90%. And then we have some price that's 100. We apply the discount, and the price will become 90, and everything is good. right? And then we say, well, public state is bad, right? Public member variables are bad. So let's make them a property. So that's code evolution for you, right? So we say, well, let's make it private. We put an underscore in front of it. And by the way, notice I have this. I should have put an underscore here and here. This is going to recurse forever. So this is going to be a correct program because it never does anything wrong. It just hits the CPU, right? So I'm going to transform this variable into a property. I'm going to provide this, the getter and the setter, and the getter simply returns price. And the setter is going to presumably say, well, you can't have something with price equals 0. So it's going to assert that a new price is 0, and everybody's happy. It just works. And indeed, the code continues to compile and run with the apply discount function, and everybody involved believes they're doing their part. The author of widget believes they're doing the right thing by doing the property. The caller of apply discount believes they're doing the right thing because they just can set the price, they can read the price, it looks like a member variable. That's the point of having properties. They are transparently replacing members, right? So everybody in the deal believes they're getting the straight deal. The caller, the apply discount, the apply discount function, they believe they do part of the deal as well because they get a double by reference and they're going to multiply by 0.9 and change it, and they're going to return happily believing effects have been executed. Yes, please.
Just briefly, it's w.price apply discount?
Is it w? No, it's w dot apply discount. Oh, you're right. Sorry, w dot price. Oh, that's awful. And I was just like criticizing one of my students. Oh, you have this typo in the slide. This is terrible. This is like you. Okay, w.price.apply discount everywhere. I'm so sorry. So indeed, we apply discount to the price of the widget, and then we expect everything to work. Code evolves. This call, well, that call with w.price.apply discount still compiles and runs, but this time you're going to get an R value from price, which is going to be duly modified by this guy, and then it's going to disappear and nothing happens. So this assert is going to fail. So don't forget, code evolution. It evolves from correct code, good code, to better code, and it still compiles and runs. There's no way to type check for that, and it's just going to fail. Not good. Did you find another typo?
No. I'm just asking, like, if I had done ref double price, the function, would that have worked?
If I did ref double price, would that have worked? Question for everybody. No. I mean, you don't want to return innards of your object. That's the point of having a property there in the first place. You don't want to kind of give away exactly what you wanted to protect because they're going to assign 0 to that. Yes? So there's a latency to the microphone working.
I think to be fair, though, this problem isn't really related to ref. You could type price plus plus and the same problem exists. This is a problem that we can't modify property. Like when there's a property pair, we can't do anything with it. So if you wrote price plus plus to increment by 1, it would call the getter, increment it, and then not reset it. I think
but that wouldn't compile.
Wouldn't it?
No.
Are you sure? I think there are constructions which you can make compile. I found them.
Those would be distinct issues, but this is not the only issue. So I have a couple more slides.
I believe you, but I'm just saying.
Okay, I would like to
Yes,
add
please.
one thing. The plus plus is defined as the spec as being equivalent to a delegate taking by ref. So arguably, according to the spec, this is the same problem as this.
Good point. All right. But let's not get stuck with this one example because there are many more. How about globals? I'm reading a global, I'm writing global. I'm not sure if it's an actual int global or a property. or a function, the two functions, right? So then I call a function with the global. I have no idea whether this is going to change global or not. But the worst case that I found has to do with indexing operators. So D has this awesome thing. The name is a bit awkward, but it's actually very descriptive. OP index, OP assign. Right? So I have I can implement things like this that actually the tensor takes care of them, which is very, very important for packed representations. So essentially, this avoids the problems that C++ has with vector bool. So vector bool uses used a packed representation, and everybody thought it's going to just work out because you use a packed representation, kind of do your syntactic tricks to make it look like you're actually manipulating individual bools, like 1 bit. But there's no reference to 1 bit, and that was the failure of vector bool in C++. And I was aware of this issue, and I said, we got to have this in order to be able to have packed vectors. Excuse me. In order to have packed vectors that allow us to manipulate vector elements that kind of go inside the vector for the manipulation and return, instead of giving the user the reference to like 1 bit, which would be impossible to do. So for an elaborate data structure that implements some sort of a packed structure, like hash table and Boolean, vector booleans, and anything that's compressed in any way that doesn't have exact reference to each component, you're going to want to overload things like op index assign, op index op assign, and that's going to go to the vector for the manipulation, not return a reference. So then when you call a function with such an object, the question is, will this change t of 0 or not? And you can't know that unless you go to the implementation of the tensor and look at it, which is pretty much which goes straight against the whole principle of encapsulation and I don't care how it's implemented thing, right? So all generic code will need to kind of be aware of this stuff from now on if we make this rule, if we implement this rule, which I think would be a failure. So, as I said, understanding the problem very well is very necessary to understanding what the solution could look like. And fundamentally, we have the problem that identical syntactic forms differ very much in semantics. So the caller passes, again, everybody in the drug deal does their part, right? The buyer gives the cash. The dealer gives the drug, but the drug was fake, right? It was powdered sugar, right? So this is the problem here. I see Attila smiling like knowingly, like, yeah, that happened to me, Sounds, how did you know that? That sounds eerie familiar here, right? So everybody in the trade believes they're doing the right things. Caller passes in what looks like a modifiable expression. The callee changes the parameter and believes they have they did their part. Both play nice, but the protocol of passing, matching parameters to arguments to parameters is failing both of them. And that's the problem, right? So, after all of this developing a better understanding of what's going on and who's at fault and what happens, here's what we think would be a possibility. So the plan is to figure out what the matching rules for for arguments to parameters are. Make sure you eliminate all the bad matches, all the powdered sugar, right? And devise code generation. So looking at the current matching rules, thank you, Walter, there are 4 levels in the D language, which are actually documented, a bit to my surprise. So the greater the better sort of thing. 1 is the easiest, there's no match. 2 is I'm going to match, but there's going to be implicit conversions, like int to long, right? Float to double, int to double, etc., right? The 3rd is match via qualifier conversion. That means mutable to const But there's a number of weird ones, which I actually have on the next slide. So whenever you can convert something to something else by simply changing the qualifiers, then you're good. And the best is exact match. And the algorithm for whenever you have a function call and you want to compute, what's the best match in an overloading set and whatever, you're going to compute the matching for each argument, and the function takes the minimum of the matching levels. So if one of them doesn't match, the overall matching level would be 1, which is exactly what you want, etc., right? So take the minimum. And there's two equal matching levels for a function call. That's an ambiguity. If everything is 1, then that's no match, etc. Changing this list would be a major hurdle. There are a few things in this world that are complicated. The Google search algorithm, the spaceship code, Boeing 737 MAX, okay, LaTeX typesetting engine, right, and C++ overloading rules. And I illustrate their increasing order of difficulty. So it's like, I remember I was in a forum on tech, and somebody said the tech page setting algorithm works well on a good day with wind from behind or something like that. So it's essentially nobody could redo that algorithm in readable code and make it work the same. Nobody. And it's very interesting because everybody keeps it's like the relics of any religion are going to be the source code I think in Pascal or some, the source code of LaTeX, which has 100 global variables and all that stuff. And, the typesetting algorithm is function that's 6,000 lines. And everybody's like, this is the function we need to preserve in the case of nuclear attack. Okay, this is because our livelihood, the humankind's ability to type math depends on that. So anyway, notice that the D algorithm for matching is not on the list of complicated things. And Walter has been very adamant about not adding numbers not changing this list. So he wanted to keep this straight. And there's been a number of attempts over the years, this could work so nice if we just added, 2.5. Okay, so changing this would be a major hurdle. We don't want to do that. To move the discourse forward, let me define two things, which is going to become kind of clear that it's related. We call a type T assignable if and only if T is unqualified or only has the shared qualifier. These types are assignable. And we call an expression assignable if there is some expression E1 such that this syntactic form is valid. And notice that this is actually I should hear kind of a syntactic expression. This would be an expression sort of before, not converted to a tree yet. Because as I'm sure you, the examples show, you can have the same syntactic form actually lowered to very different things, which for example, w.price. If you have w.price in an assignment, then it's a function call. If you have w.price in an assignment on the other side, it's a different function call, right? So I have a syntactic form that looks like an expression, and if you can actually assign to the same syntactic form, then we call that an assignable expression. And these definitions are important because guess what? The bad situation is when you have a ref to an assignable type bound to an assignable expression. So that's the one bad situation that we want to eliminate. Whenever you have something that looks like a reference but it's not, when you have a type that is assignable, when there's this disconnect between the parties in the transaction, then that's the problem. Just to show you the qualifier conversion rules for a second, I'm very proud of this. This is like the one thing in the D documentation that I'm super proud of. I wrote this. And it's actually on the website, and it shows the complete graph of implicit qualifier conversions. And as I told you, it's more than just const and immutable. There's like a lot of nonsense here. This would be like mutable, no qualifier. It converts only to const, but we have like in, out, and all that stuff. We have immutable goes both the non-shared and the shared way. And anytime there's a path in this graph, it means there's going to be a qualifier conversion that's possible. But notice that the only combination of qualifiers that are modifiable are this guy, no qualifiers, and shared. Everything else you cannot assign to. So that's why in my definition we call the type assignable if and only if it's unqualified or has a shared qualifier. This graph, this picture shows why only those two have, because all others have impossibility to assign to. Cool. So at this point we have a fork in the road, and it's up to us, the entire community, to figure out what would be the best way to go. I have a fork in the road for binding rules. To bind expression E of type U to reference to T, proposal 1 goes the following way. If E is an assignable expression and T is an assignable type, this will be the potential bad case, then return existing matching algorithm, and we're done. So if the situation is potentially bad, then go with the conservative previous way of doing things. So that eliminates the bad case. It's going to say, I can't do this, I can't do that, right? But here's the relaxation. Otherwise, run the existing algorithm, assuming E is an L value. This is the key relaxation here. And we're going to get some level X. And if X is no match, then I'm going to return no match. In all other cases, I'm going to return level 2, which I remind you is match via a conversion, an implicit conversion. So that means the following. Here's the intuition. The intuition is we want to eliminate the confused case of assignability, and that would be the first part. But we want to make binding to ref count as a bit of a difficulty. So it's a conversion. So it's like, whenever you want to convert something to a ref, there's got to be a difficulty there. And that allows us to overload on ref. Because whenever you have ref, it's going to count as an exact match or a match via qualifier conversion. But whenever you have an R value there, it's going to be more difficult. It's going to be an inferior level match level. So that's why I return 2 here, nothing better than 2. Let me remind you here. This can get a bit hairy if you don't keep this in mind. So these are the levels again. And this and that are bindings of L values to ref. So exact match is I have an int, I bind it to a reference to int. And this is I have an int, and I bind it to a reference to const int. Right? These are levels 3 and 4. And whenever I want to bind an R value to a reference to something, I want to have a worse matching level. So I need to have like a 2, or 1 is no match, but I need to have a 2. That's why I return 2 from there, because these are what makes overloading of ref works, and that's how we avoid the C++'s mistake. Okay? So again, if I put anything more than 2 here, R values are going to trample all over binding to ref, and I can't overload on ref anymore. I can't overload on int and ref int with ease. It's going to become impossible. So that's why I kind of cap this matching at level 2. All right, so I think this is a simple enough rule. It's not adding LaTeX level complexity to the whole algorithm. It does not add new levels. It doesn't mess with anything, and it just relaxes the things that need to be relaxed. So let's take it for a ride. And getting back to Bjarne's example, we have bump of takes along by reference and increments it very nice. I have an int counter. I bump the counter. No, this is an assignable expression. right? So I'm going to go with the old algorithm, and the old algorithm is not going to accept that. Cool. Then I'm going to call bump with literal of type long, and it's going to match at level 2 because it's not assignable, right? It's going to go level 2, all good. I'm going to even call it with a constant type integer, and again, it's going to match at level 2, and everybody's happy. Because here, again, this is not assignable, so it goes this way here, and it's going to run the existing algorithm, assuming EL value, and it's just going to work. Very nice. We have, yes, please.
I'm confused. Why is it okay?
I'm a bit confused on this. Why is it okay to do bump on a constant like here?
Why is it okay to do a bump on a constant? Yes, please.
It's not an assignable expression.
Because it's not an assignable expression. Because the caller understands they're not going to bump the constant 100 for the rest of the program. So it's obvious to the caller that they're not interested in modifying the literal. Right? This is the point. This example makes it obvious that it's silly code, but it's not code that somebody may reasonably assume something that's not happening. Right? In this case, it's a small type, but what if this were a large type? And then there would be clear that it's a performance thing. So yeah, in this case, silly but unambiguous code. Silly but not confusing. Steve.
Yeah, so you have an integer being passed, an integer constant being passed. Wouldn't you consider that to be an L value integer? Which would be the same as bump counter, wouldn't it?
Here?
On this bump 100 without the L.
Yeah, this guy.
So if it's not assignable, it's the first rule. Okay. That's not
Well, I have bad news too. No, wait, more good news. I'm the wrong slide. Overloading on ref still works, and that was the point of the entire algorithm. Overloading on ref works because whenever you have like fun42, we're going to have 2 overloads. This guy is going to match at level 2. Remember, we kept matching at level 2. And this guy is going to match at level 4 because it's an exact match. Yay, right? So this goes the right way. Super nice. And then I have an L value of type int, and this is going to match this guy at level 4, exact match, and is going to match this. And this is going to match at level 2. So this is existing rules. The existing rules are going to go for these overloads. Boom. This new rules are going to go for this guy, and they're going to be capped at 2. So overloading on ref works very nice, and this is like a primary concern of this proposal. But there are quirks. What if I have a fun that takes a reference and a value, and I have an int that I just put a const on? And we know that const int converts to int, but that counts as a conversion. It's not implicit. It's just it's an actual conversion. It's not a qualifier conversion. So in that case, we have a level 2. We have 2 matches at level 2. The algorithm doesn't know whether this would be preferred or that. And when you try to overload on ref and rvalue and also kind of add some qualifiers in the mix, it can get confusing. Not confusing, but unpleasant, let's say. Walter says it's unintuitive. For example, I have a function that returns, that takes an int. I have a function that returns an int. And this should be like return int and take void. So whenever I have a fun of gun, then I'm going to have an ambiguity here because this is going to return a const int. Oh, why is this? Oh man, I have like this. I overload the names too much. Fun, gun, and hun should be. So essentially, whenever I call a fun with a const int, I'm going to have, well, which are going to take? the reference to constant for an R-value constant, or are you going to take the conversion from const to int? And we have two level 2s here, so that's ambiguous. Okay, this is ridiculous. So this should be Han, and this should be Han. It works, but it's perverse, right? This is not politically correct code, okay? The HR would have a word with me, okay? It's not. This should be Han, this should be Han. Han returns a const int, and we have an R value of type const int. Where does it go? It can go to both according to the algorithm with equal propensity, right? So a possible response would be, why are we in the business of overloading simultaneously on ref and qualifiers? Who does that and why? And take that person to HR, right? Send them, that they have a problem, not us. I assume these issues can come in code evolution, like I mess with like a ref versus R value and qualifiers and whatnot as I'm developing code. So it is a real problem. For that, there's proposal 2. No changes to parameter level matching, same exact algorithm. But we change function level matching. Remember, functions take many parameters. And remember, the old algorithm took the minimum of the matching levels. So the old algorithm was min of all parameters. And the new algorithm goes like this. Run the whole algorithm once, assuming all L values, and get all matches. So this is relaxed. So it's like, you know what? Yeah, forget that there are values, make them all L values, and see what happens. And you get matches. If you get one match, then you're good. If you get more than one match, then discard that result and defer to the old function level algorithm, thus eliminating ambiguities. So that's going to be very much backwards compatible. It's going to allow us to make reference and value interchangeable whenever we evolve code, so that's a nice property. However, the rules have become quite a bit more complicated. Literally what we do, we add a new matching level without adding a new matching level. Because what we do is like run the algorithm assuming something. Oh, too many matches. Revert, run the algorithm again with different assumptions and see what happens. So that would be the major disadvantage, that this is really an algorithm that adds a new matching level by complicating the function level matching. And it's also slow because it runs the whole algorithm twice, but Walter looked at the code, he said it's practically not going to be a problem. So that's sort of a minor concern. I think the major concern is complexity. So not very happy about that. Before we move on to Cogeneration, I would like to take a vote by rounds of applause. Proposal 1. Let's hear the decibels. Could you measure the? Okay. Who is for proposal 1 by measure of applause? Okay, golf clap. Who's for proposal 2 by round of applause? Oh, that's. That was less than a golf clap. It was pool clap. Yes.
Is it possible that we are overcomplicating this? Is it possible that we are somewhat overcomplicating this? And I think the goal of this was to have more efficient parameter passing for annoying types, right? Or just might it be an approach to like changes at the type level, like declare a type as we want this to be passed efficiently, and then if the function wants to modify it, it's implicitly in the back end passed by reference, and if the function wants to modify it, it has to make a copy on its stack, which is not going to be any more expensive anyway.
Just to make sure I understood, so make it transparent, pass by reference. We actually thought of that, and aliasing is going to kill you. Thank you. Aliasing is just, whenever you pass by reference in a hidden way that the user doesn't understand or see or know or can control, then you're going to have you pass an alias to the thing, you pass another alias to the thing, you pass an alias to a part of the thing, and it's just a mess. So we couldn't make that work. Okay, so I heard a golf clap for the first and like a, I don't know, a bad golf shoot clap for the second, so to be noted. So let's look a bit at code generation. So how do you generate code? Yes, please.
Can you take advantage? Testing. Any chance to take advantage of the const system to avoid that? Like
Of
if you
the
know that
const?
the original value will never be written to, it's immutable, or it's
We do take advantage here. No. We do take advantage here. So we take advantage by eliminating exactly things that can be written to from the phrase. So this is exactly where const and all that immutable and thank you. Great. This is exactly where we leverage the type system for, well, here's how we detect very accurately the bad case. Yes, please.
It doesn't. Okay. Is considering the proposal one, but just with dropping the idea of assignable expression, like has it been looked at, and what would be the problem with that?
Can we have proposal one by dropping the assignable expression part?
Yeah, just considering assignable type instead of the union of the
All right, let's
or the
take a look.
intersection.
So we don't check for assignable expression, right? Okay. Let's see. This is gonna not right. This is gonna be a problem because T of 0 in generic code is unknown whether it's a reference or an rvalue, right? And it's assignable, as I can clearly see from the surrounding code. So this would be the problem essentially. Do we want to live with that or not is the question, right? Thank you. All right, so moving forward to code generation. Where are we? Okay, code generation. So there are two issues here. Number one, lifetime of temporaries, which turned out to be a large part of the proposal. So this binding is going to happen like, well, you're going to create an rvalue by some means of calling a function or expression or whatnot. It's going to create an rvalue. Then you're going to bind that guy to a ref. Obviously, the rvalue must outlive the call to the function. So, it turned out that this lifetime of temporaries became a large part of the proposal. And as I was working on that, turns out it's another evaluation issue too, so in what order things are done. So these two issues needed to be solved before we had a good idea on how to generate code. And the main problem was we are having a severe underspecification problem. So if you look at the documentation, you just can't tell. Look at the documentation. I have no idea what's going on when things start to live and when things and living. So we figured out the rules are quite complex, and the dip grew significantly. So we had like a larger and larger dip that included essentially like documenting what happens already for the most part. And here I applied the very interesting tactics, which was migrate stuff to the specification kind of independently of the dip. So the proposal would, so you write a proposal and you go, oh, this is existing behavior that's not documented. Don't document it in the dip. I went, well, let me actually update the specific by means of pull request to the specification, like simple. Update the specification and then make the dip use the specification. So modularity, if you wish, right? I don't know, refactoring. There's a question. Okay, so just document what's there. It's turned out to be extremely successful. And I gotta tell you, there's no way of doing this without looking at the code. You gotta look at the compiler source code. Yes, please.
So the problem with this is how do we distinguish now between this is just a thing that the compiler does, or this should actually be the way that it should happen? Because once migrate from compiler to specification and from specification to compiler, there is no one single source of truth anymore.
The single source of truth should be the specification. Because somebody should come and be able to implement a compiler using just the specification. I hear chuckles. Why the chuckles? All right, so just document what's there. And it turns out what's there is quite gnarly. So the diff says whenever binding to ref parameters, temporary follow the same exact rules as if you were binding to rvalue to value parameters. So this is the only sentence, the only paragraph in the dip that deals with that kind of stuff is like do whatever you would do with rvalue matching. So essentially we're done. The dip is done in one sentence with all of the lifetime of temporaries. What happens, everything that should happen is like whenever you bind to ref, because this is done and it's done well because it's been working for years. Yes, please, Walter.
The reason it's been working for years is I struggled with that with the C++ compiler, and I got it to work, and I didn't see any reason to invent a new way of doing it.
I think that's a very good strategy. And again, as I mentioned in the Ask Us Anything, I think a great merit of C++ is that it specifies everything that's going on. So very nice. So binding to reference parameters follows the same rules. Those rules are not easy, though. They are subtle, and I actually have okay, you were not supposed to see that yet. You know the joke with the Google search history? Okay, so let me make this larger. That'll be order of value. Okay, this is lifetime of temporaries. Where are you? You didn't see that, okay? Lifetime.
It's the third one.
There you go. I don't have my glasses, so I just wouldn't want to admit that I need glasses here. All right, so lifetime of temporaries. Oh, is it even visible? Okay. Okay, so lifetime starts whenever the expression is evaluated, which is obvious. What's not obvious is the whole short circuit thing. It turns out that one day, it started like this. One day, Walter woke up and he didn't feel like good. And he said, you know what? Whenever I evaluate an or an and expression, those with that short circuit, whenever something happens in the first part of the expression is going to last through the lifetime of the expression, but whatever is on the other side of the expression is going to last until only that side is done, until you get it to Boolean, and then you destroy everything that was created in that part of the expression. He could have done it the same way for the left-hand side of the expression and the right-hand side, and that would have been uniform. But he said, you know what? No, I'm just going to do it like this. I just don't feel like it this morning. The coffee tastes terrible. I don't know. So there's some event in our community's life that led to this. And, well, it turns out that whenever you create a temporary on the right-hand side of a short-circuit evaluation, that guy has a different lifetime rule. Right? Fine. And order of evaluation. Yeah. Order of evaluation. This is actually quite a bit more easier and more intuitive and easier to understand. So this spec I wrote, I made sure that everything is in there with Walter's help. Walter had to look in the compiler code to say, oh, I remember how things live and how they die and that kind of stuff. All right, so and then it was simple for the dip. It was easy. And we have huge simplification on all sides, implementation, understanding, use. The rules were complicated. So, if we took a dip that had just slightly different rules, it would have been like, like the Tsar's finger, the legend. The Tsar drew with a train line between Moscow and St. Petersburg, but his finger was in the way. So the road took a bump. and they built the thing to the spec. And it would be like the deep said, all temporaries must live through the end. So whenever there's a ref, we're going to do the ZARS thing. And otherwise, by the way, that's an urban legend. It didn't happen that way, but it doesn't matter. So, anyhow. Lesson learned, 3 lessons. Number 1, the motivation is the rocket fuel pushing the deep forward. Unless you motivate it properly, it's not going to gain interest. So motivate it properly, and I can't thank Manu enough for badgering us about this with examples, with issues, with stuff. Yes, golf clap for Manu, please. Thank you. But Chesterton's fence is essential too. Do not remove a fence if you have no idea why it was erected. Okay? So a lot of ideas were vehiculated without an understanding of what's the problem with C++'s way of doing it, what's the problem with Rust's way of doing it, and those are not viable. So don't forget, rules are broken once you understand them, and you get to actually find good solutions to things. Number 2, integrate within. We have an under-specified language, and the deep has 2 roles, improving the specification and adding something to it, right? So make sure you modularize, improve the specification separately, what exists, make sure it's documented, and then you're going to build a deep on top of that foundation. Otherwise, you're going to build on sand. It's not going to stay. So vague, vague deep, vague specification, not good. Number 3, assume your deep will be implemented by a vengeful X. But they are principled. Anything that is in the deep and they don't do, it's a bug on their part. No, they want to show you are a jerk. You are the bad person, right, in the relationship. They want to show you are bad. So assume the deep is going to be implemented by a very principled, very smart, very capable X who would want you to see dead and see your guts spilled, okay? Whenever you make a mistake, anything that's imprecise, they're going to interpret the worst way possible. All right? So we don't want this kind of dips that are kind of, assume a friend is going to work on this. No, assume your worst enemy is going to work on this, okay? Thank you very much. How much time for questions here?
Yeah, what do you reckon? 1 question, 2 questions? 1. 1 question. Make it a good one. Who's got a really good question? Oh, there's only a request to understand what the boat was about.
Oh, the boat. Thank you. All right, so the Kon-Tiki expedition in the 80s. They built a boat by the specification of the ancient Egyptians. And it was made of, what's this? What? Reed. Okay, so it was made of reed, and it was like the exact specifications, but they said, you know what? There's a rope that takes, like it's tied here, and it goes here. Somewhere in like the first third of the boat. There's a rope that goes that way. And they built a boat, and they noticed that the rope would not actually help anything. And it was kind of in the way, so they just eliminated the rope. Guess what? 1 month in, this part of the boat started to sink. So like, oh, so those idiot Egyptians, they did have an idea. So the next version of the boat, they put the rope in. Let me show you the design here. So the next edition of the boat, they put the rope in, probably. Right? So, that's Chesterton's fence applied. Okay, thanks again. Thank you.